Okay, let's go ahead and get started. It is my great pleasure today to welcome Dr. David Hathaway as our speaker. Dr. Hathaway received a BS in astronomy in 1973 from the University of Massachusetts in Amherst, an MS in physics in 1975, and a PhD in astrophysics in 1979, both from the University of Colorado in Boulder. He was a postdoc fellow in the Advanced Study Program at the NCAR Research Center in Boulder from 1979 to 1981, and then moved to Sunspot, New Mexico, where he was an assistant astronomer at the National Solar Observatory. In 1984, he moved to Huntsville, Alabama, where he was an astrophysicist at NASA's Marshall Space Flight Center and served as the head of the solar physics branch from 1996 to 2010. In July of 2014, he relocated to NASA's Ames Research Center in Moffett Field, California. He has received dozens of awards from NASA, including the NASA Inventor of the Year Award in 2002 for Video Image Stabilization and Registration, aka VISAR, and the National Exceptional Scientific Achievement Medal in 2014 for his discoveries of the sun's shallow meridional return flow and giant convection cells. He retired from NASA on December 31st, 2016, but still continues to work on his areas of interest, which include observing, modeling, and predicting the sunspot cycle, understanding the magnetohydrodynamics of the sun's interior, and how it produces the sun's atmospheric features. Today, Dr. Hathaway will be giving us a seminar about solar polar vortices. Welcome, David.
All right, thank you, Lisa, for that wonderful introduction. Let me start by sharing my screen and starting the talk. Again, solar polar vortices. This is work I've done with Lisa, so it's a little odd that she introduces me since she's a part of the talk, but nonetheless, Lisa's been very much a part of this from work we started doing on this back in the summer of 2012, I believe. I also need to acknowledge Sushant Mahajan, who was my last summer intern in 2016 at Ames, and he got into the nitty-gritty details of what we were doing and found several problems, and we found solutions to those problems. So a lot of what we've done here, improvements we made, are due to Sushant. Here's a brief outline of what I'm going to talk about. I'm going to start with describing the sun's photospheric convection spectrum and its characteristics and features, and then briefly touch on different methods for measuring these large-scale flows. We end up using local correlation tracking of the Doppler velocity pattern due to supergranules as the method. What we find for the giant cellular flows are polar vortices at higher latitudes and Rossby waves around the equator, and my phone is going off. Sorry about that.
Usually it's the audience.
Yeah, I know. Let me, and it won't even let me get in to kill it. Let me put it on airplane mode, and we should be good. All right. Polar vortices and equatorial Rossby waves. I'm not going to talk about the Rossby waves so much today. Without a doubt, they will have diagnostic properties that tell us about flows in the interior of the sun, but today I want to concentrate on the polar vortices in particular. I will spend quite a bit of time describing their hydrodynamic properties and then briefly get into their magnetohydrodynamic properties. So let's start with the photospheric velocity spectrum. This is a work, bits and pieces I'd done previously, but the culminating paper was with Thibaut Thiel, Amy Norton, and Irina Kitiashvili in 2015. We analyzed and did data simulations of the Doppler velocity data from HMI to determine the spectrum of the flow velocities for all three vector components. And it's not point by point the vector component, but globally, how strong is the radial velocity as a function of wave number, the poloidal velocities, these are flows with divergence, horizontal flows with the divergence, and then the toroidal flows, horizontal flows with curl. The ultimate figure is shown here. There's a black line going across the top of all of these different components that represents the total velocity. It's a function of the spherical harmonic degree or wave number. It's a rising spectrum. For the most part, there is a peak at wave number about 120 that represents supergranules, dip down or leveling off, and then another peak at wave numbers of about 3,000 representing granules. Again, the fact that it's rising with two features for the part that we're looking at, which is the lower end, it's just a rising spectrum. So what you're going to see depends upon where you cut off that spectrum. You will be dominated by the size of the flows at your cutoff in wave number. The colored lines represent the different components of the flow velocity. The radial flow component is shown in green. It's fairly weak, except for when you get up to granules. The poloidal part is the part with the divergence and convergence. That's shown in red, and that's what you see in supergranules and granules. The blue line represents a toroidal velocity. So these are the velocities that have curl and no divergence. And that component dominates at wave numbers below about 30, which is the region we're going to be interested in. There are a number of different methods that can be used to measure these giant cellular flows. First that comes to mind and probably was used first is helioseismology, basically tracking acoustic waves. These are radial oscillations, so the signal is strongest at decenter. Two of the primary methods for doing local helioseismology are time distance, where you correlate a signal at one point with acoustic signal at distant points, and ring diagram analysis, where you do spectral analysis in horizontal and in time to get rings where the offset of the ring gives you flow information. You could also track magnetic elements. Here again, the signal, since the fields are primarily radial, is strongest at decenter. You can track granules in the intensity signal from HMI. There again, the signal is strongest at decenter. Limb darkening and foreshortening makes it hard to track them closer to the limb. Tracking supergranules, the Doppler signal in supergranules is strongest at the limb. So even though you have foreshortening, at least the signal is strong there. So all of these are useful, and they all unfortunately have systematic signals that need to be characterized and accounted for. The Doppler signal at least has its strongest signal near the limb, and therefore gives us better access to the polar regions, which are, from our viewpoint here at Earth, are always near the limb. Tracking supergranules, something that people have done for many decades now. The Doppler velocity from the horizontal flows has its own idiosyncrasies, though. In particular, there was this super rotation of supergranules that was discussed, and then I hope ultimately realized that it was a projection effect. But if along the equator, of course, the actual vector velocities are multiplied by the sine of the longitude from the central meridian. Jesper Sko showed in 2003 that you could largely remove this effect basically by dividing by the sine of that angle, but you don't want it to blow up at the central meridian. So he came up with this formula, which is take the sine of the angle and then the square root of sine squared of longitude plus 1% solution. They keep it from blowing up at decenter. So if you do that along the equator and take Fourier transforms in longitude and time, you can determine the rotation rate of the supergranules as a function of their sizes or wavelengths. And the plot shown at the bottom here, the black dots with error bars are measurements of, it's a function of wavelength for the rotation rate of the different cellular components along the equator. The red dots are measurements from global helioseismology of the rotation rate at the equator as a function of depth. And it shows the surface shear layer where the rotation rate increases as you go inward to a depth of about 50 megameters and then drops off after that. And you see, looking at this, that that follows very much the rotation rate that you see for the supergranules themselves. I did a data simulation where I produced supergranules and then deprojected them the same way I did with the MDI data. Those results are shown with the open circles in here. And the solid line is the input profile that I put in. So we can basically reproduce this effect with the data simulation. The important thing here is that supergranules are advected by flows in the surface shear layer at depths equal to their widths. Typical supergranule of say 30 megameters width is advected by flows at 30 megameters deep. There's no doubt it extends deeper than that, but it's steered by flows at 30 megameters deep. If we don't deproject it, which is, you can only do that along the equator. So if we don't deproject it, instead look at cross-correlating. First of all, if you don't deproject it, you get the plot that's on the left, which shows with the black dots that the supergranules seem to rotate faster and faster and faster. And this was early on thought to be a super rotation of supergranules where they're moving faster than anything inside the sun. These two plots show that this is due to projection. It's due to the way the vector velocities are projected onto the line of sight. On the right panel shows basically the same data, but now we're cross-correlating the signal to find out how fast it is. And again, here it's relative to the Carrington rate at the equator. And the important thing to see here is that at say a 4-hour time lag between two Dopplergrams you're cross-correlating, you get about a 40 meter per second faster than the Carrington rate, and that corresponds to a rotation rate at a depth of about 20 megameters. If you go to 8 hours, it's a little faster, corresponds to a depth of 30 megameters. 16 hours, it corresponds to a depth of about 40 megameters. So if you go to longer and longer time lags, you are basically filtering out the smaller, shorter-lived cells and are dominated by the larger cells that extend to deeper depths. So we can use the supergranules to probe this surface shear layer and flows in the surface shear layer, and in particular here to probe the changes in structure of the giant cellular flows with depth. All right, so to look for these giant cell flows with the Doppler data, there's a fair number of steps we have to do in preparing the data. We start by acquiring the 722nd averaged Dopplergrams from HMI every hour on the hour, which I've been told was a bad choice of times. Nonetheless, for the most part, that data is available and perfectly fine. From that, we have to remove the known signals, the spacecraft motions, parallel to the equator, parallel to the rotation axis, and towards and away, and then remove solid body rotation. I then have a program that determines and removes the solar signals that are stationary on the disk, the convective blue shift, the differential rotation, and meridional flow. After doing that, removing all of that and averaging together, there are instrumental artifacts that remain. That's shown in the bottom image on this slide. So we, after determining those instrumental artifacts, those are subtracted from the data at each point, and you go back and redo step 3 to produce the cleanest possible image of just the Doppler signal due to supergranules. The data is mapped into equirectangular heliographic longitude and latitude. Using a bicubic interpolation, we go from 4096 images to 4096 squared maps. That's overkill for looking at giant cells and for seeing supergranules. So we smooth it with the 2D Gaussian and resample at 512 by 512. So the actual local correlation tracking we're doing are on 512 by 512 maps of the Doppler velocity due to supergranules. Lisa and I did this with a summer intern back in summer of 2012, published in 2013, Owen Colgrove, who went off to do some other kind of physics. In that, we used a circular correlation window, size shown here, and used 8-hour time lags, 16-hour time lags, and 24-hour time lags to try to look for the giant cellular flows. In that method, we did the local correlation tracking with this circular window at an array of 256 by 256 longitudes and latitudes. From those local correlation maps, we removed the longitudinally averaged velocities, the differential rotation and meridional flow, and then average those maps over a Carrington rotation using the Carrington longitude and latitude given for each of those individual maps. We've improved on that method in a paper Lisa and I published last year. First of all, thanks to Sushant's studies, we changed the correlation windows to be wider and the search areas to be broader in looking for the peak in the correlation. We improved the method for measuring the fractional pixel shifts in the correlation peak. And then rather than removing the longitudinal average of the stationary flows, we removed the disk average. And you'll see that they, on the disk, it depends upon longitude. So this is a better way of getting rid of the flows that aren't giant cells. Finally, we actually measured the differential rotation of the giant cell pattern and use it to construct synchronic maps as opposed to Carrington maps, representing a single moment in time. In particular, we do this on a daily basis. And so we have a map of except for the extreme high latitudes, a map of the entire sun every day. All right, so this illustrates some of those improvement methods. Again, the old method, we used the circular search area. Now it's expanded with latitude so that the physical area under it, basically the number of supergranules inside that window stays the same regardless of the latitude you're at. And we extend the search area that previously we, just to speed things up, we searched in the obvious place, which is where differential rotation would take the supergranules, and didn't do much around it. But there, it meant that the distribution of our measurements, which should look Gaussian, was truncated on one side or the other. So the average, of course, is thrown off. So we try to sample the full distribution of velocities. Another thing that Sushant found was something called peak locking, and this is known in other communities that try to track things in fluids by correlation tracking, that you can try to get a fraction of a pixel shift by fitting a Gaussian or running a parabola through the peak in your correlation. And it turns out that doing that, there's still a tendency to avoid half pixel shifts. So these two histograms show the distribution of flow velocities, and you can see what turns out, single pixel shifts are the peaks and the half pixels are the valleys, that there's a tendency to miss that. We solved this by using a bicubic interpolator to shift the reference data, the patch that you're going to correlate to, by that fractional pixel. So we determine the fractional pixel, shift the data by that fraction, and try it again until you're basically at integer pixel shifts. And so this works very well. You can see the distributions now don't show the effects of the peak locking, and it gives you accuracy to about a 20th of a pixel. All right, so we do individual hourly measurements. So we take one of the 512 by 512 Dopplergram maps and correlate it with one 4 hours, 8 hours, or 16 hours later to determine flows across the disk, again with 256 by 256 positions across the disk. So here's an individual. It really is literally a typical individual map. You see for the longitudinal velocity, the differential rotation with it slow at high latitudes and fast at the equator. You can see a little bit of the meridional flow, that the southern hemisphere is bluish or towards the south. The northern hemisphere is reddish or towards the north. And you see a modeled pattern in there. We construct initial flow maps by doing what we did before, which is basically Carrington maps, but it's basically using the Carrington longitude for each of these maps and averaging the data in over full Carrington rotation. So given a date, plus or minus 14 days from that date, you average the data together and you get these what we call the initial maps. We remove the disk average flows, and those are shown on the bottom here. You can see that there's differences in longitude in the flows. So our old method of just removing the average left behind stuff that was fixed on the disk but appeared to move from day to day when you average it in with other data. The meridional flow is a particularly complicated pattern. So it's this signal that we remove from these individual ones before averaging in to produce these initial flow maps. I call them initial because they have used solid body rotation at the Carrington rate, and we know that these giant cells don't rotate as a solid body. We can compare these maps with maps in particular. Bogart, Balder, and Basu in 2015 did a ring diagram analysis, found a similar pattern. There's a funny story about this. I won't go into it now, but you can see here that in particular at high latitudes, the high latitude structures are, pretty much one-to-one. You can pick out the same features in each of these. One using helioseismology, ring diagram analysis, and in our method by tracking supergranules. Again, we want to make the maps better by averaging using the differential rotation of the giant cell pattern. So what we did was take the initial flow maps and cross-correlate them with a 28-day time lag. And you get this average correlation map shown shown here, and you can see the positive ridge representing the rotation rate of the pattern. It's nearly rigid rotation at the equator between plus and minus 30 degrees or more, almost right at the Carrington rate, but then differential rotation at higher latitudes. There's a blue line going through here, which is the peak of that correlation, and then a white line, which is a third order polynomial in sine squared latitude fit to that. And so that represents the rotation rate of the giant cells. And so we want to use that to better position the data when we average it together over more than a rotation hour. It turns out at high latitudes, it's about a 34-day rotation. So to fully get all longitudes at the high latitudes, you need to go plus or minus 17 days from the date in question to fill out all longitudes at the highest latitudes. So here's a comparison of the initial map on the left and the map with the differential rotation used on the right. The central meridian for both of these is at about 164, so they should agree almost perfectly there. What you can see with the new method is that at higher latitudes, you bring in features that weren't even there in the other map because you hadn't allowed enough rotation of the sun, namely 34 days, to see all longitudes at that latitude. So this brings in, what's at the extreme edges in longitude at the highest latitudes this way. All right, so again, this gives a much cleaner signal. Here's a comparison of the data we used in the Science article in 2013 versus the new method. You can see that it's smoother, not so spotty, and again, there are a number of improvements by including all longitudes, in particular at high latitudes. All right, so from that we construct daily maps using data from plus or minus 17 days from the date in question. The nice thing about these maps is, again, that at all latitudes, the flow velocities match at 0 and 360 degrees. They don't in the Carrington maps. You see here two different dynamical regimes. You see the equator, where it's almost the solid body rotation, where there's not much motion, and you see the high latitudes where the features are moving to the left and are being sheared out by the differential rotation at those latitudes. We can determine the cell shapes by doing an autocorrelation of each individual map at different latitudes. And that's shown here, that at the equator, the autocorrelation shown in the center panel, and you see that the features there are roughly circular, whereas at high latitudes, 60 degrees north on the left and 60 degrees south on the right, the features are elongated. They're a spirally type pattern going into the poles. So different regimes entirely. Again, the low latitude features are Rossby waves. They have a well-determined dispersion relation to show that they are. And again, I'm looking forward to seeing what can be done with them. The flows that we find are heliostrophic in the sense that they are not diverging and converging, but rather cyclonic and anticyclonic. And you expect this from a balance between pressure gradients and the Coriolis force, for a rotating object where the flows have lifetimes longer or comparable to the rotation period of the object. So here's a long movie. I'm not going to show the whole thing. I think this is 10 years of data. The equatorial view, you see the features don't appear to move much, certainly, whereas when you look down on the pole, you see these spiral structures, chains of vortices of the same sign that connect up to each other and spiral into the poles. There, you'll also notice what looks like in particular in the polar view, this adjustment that rotates once a month. That's basically the far side of the sun for the given image, and that's the piece of data that's most uncertain. It's 17 days different from the point you're at, so the flows have changed a little bit there, as that is basically gets adjusted as it rotates around, and you get a better view of how it has changed. So again, I'm not gonna show the whole thing. We're 3 years into the 10 years here. It's pretty much the same thing all the way through. You see in particular the polar vortices form these chains of vortices that link together and spiral into the polar regions. All right, so let's look at some of the hydrodynamic properties. One thing we can look at is kinetic helicity. The helicity is the dot product of the velocity with the vorticity. We can get a proxy for one component of that, namely the radial component. We don't have radial velocity, but we have a proxy for it, which is the divergence of the horizontal velocity. So the kinetic helicity signal here is the average of the divergence of the horizontal velocity multiplied by its curl at all latitudes, and you see individual measurements in there. The different dots are from individual measurements. The key thing is that it's one sense in the northern hemisphere and the opposite sense in the southern hemisphere. We can also measure a Reynolds stress, which is shown on the right. And this is the correlation of prograde velocities with southward velocities. And you see that, again, near the equator where the Rossby waves are, it's pretty flat. But when you get up in the polar, the higher latitudes, it's positive in the north and negative in the south. So this is an equatorward flux of angular momentum. And this is Reynolds stress that you need in order to maintain and perhaps produce the latitudinal differential rotation on the sun. We can also look at both differential rotation and meridional flow. So on the left is the differential rotation. That black line is actually a cloud of thousands and thousands of black dots that all pretty much fall on top of each other. The red line through there is the rotation profile that Lisa and I get for the magnetic elements, which are representative of a depth about halfway through the surface shear layer. But you see in particular at the equator, they totally disagree. And also at higher latitudes that the giant cells are rotating faster at higher latitudes than the magnetic elements are. The meridional flow is shown on the right, again with a cloud of measurements from years of these maps, and I think 256 different latitudes. And you see that it's northward in the north and southward in the south by about something like 2 meters a second towards the poles. There may be torsional oscillations in this. I show this just to pique your curiosity. On the right is what we get from the magnetic elements for the torsional oscillation signal, which is slowing down and speeding up of the rotation at different latitudes, clearly related to the sunspot cycle. On the right is doing the same thing for these giant cell flows, which is remove the average differential rotation and look at the residual as a function of time. Could be that there's a signal in there. I don't know. Certainly it's the lower latitude where the Rossby waves are. There may be something there. The higher latitudes, I don't know. It's pretty noisy. All right. If we look at the differential rotation versus depth, and so on the right, I have a plot from Howe et al. In 2000 of the rotation rate as a function of depth at different latitudes. And I've placed on there red dots for the magnetic elements, which is the rotation rate at those latitudes for the magnetic elements. And they often match up at two different places, except at 60 degrees, where it only matches up at one. Clearly here, at all latitudes, it matches up at a depth of about, 3 or 4% of the way into the sun. So about midway through the surface shear layer. The blue dots represent the rotation rate of the giant cell pattern. And at the low latitudes, there's perhaps a match near the surface and a match near the base of the convection zone. As you get up to the higher latitudes, 45 and 60, the only place it matches is at the base of the convection zone. So this suggests that the polar vortices we're seeing are advected by the differential rotation near the base of the convection zone. So if you do the same, take that information and ask what that means for the meridional flow, it suggests that the meridional flow at the base of the convection zone is towards the poles. Since it's the same cells that are moving, they're moving with the rotation rate representative at the base of the convection zone, and they're also moving poleward. So this suggests that there are two cells in radius, a poleward flow near the surface, equatorward return flow at the base of the surface shear layer that extends deeper in, and then a poleward flow again at the base of the convection zone back towards the poles. All right, we've done spherical harmonic spectra of these cells. This is the average spectrum shown for the poloidal component on the bottom and the toroidal component at the top. So we look at the curl and the divergence of the horizontal velocities and do a spherical harmonic transform on those. You can clearly see that the toroidal component is the strong one. So these are flows that are largely toroidal. Within that signal, you see two concentrations. You see concentration along the edge of the diagram where M is equal to L. And those are the Rossby waves. And you see a concentration at along the central axis at M equals plus and minus 1 and maybe plus and minus 3. So those are the polar vortices. So there's evidence in here of these two distinctly different regimes on the sun. Since we do these measurements at 3 different time lags, we can get some idea of how those flows vary with depth. So here are examples of the flow maps themselves at 4 hours on the left, at 8 hours in the middle, and at 16 hours on the right. And as I showed early on, these are representative. Since we're tracking supergranules, these are representatives of depths at 20, 30, and 40 megameters within the surface shear layer. If we look at the spherical harmonic spectrum of that, we find that except at 6, certainly below wave number of about 10, the spectra are virtually identical for all 3 time lags, for all 3 depths. The 4 hour and 8 hour agree all the way out to the edge of this. Part of this is that we're really sensitive to wave numbers more like 15 and below or 20 below, you know, given the aperture that we have. So we are not well resolving the features at the degree of 30. But the key point here is that these spectra are virtually the same through that surface shear layer. So it shows that the giant cells are unchanged through that, and again fits in with the idea. Whoops, that I didn't do that. Fits in with the idea that they are deep cells that extend, in fact, all the way to the base of the convection zone. All right, the final thing I wanted to show was an indication of what these things do to magnetic field. What I've done is placed quarks basically on the surface of the sun and allowed them to move with the giant cells flow velocities that I have. I've superimposed where they are on magnetic maps of the sun here. So this is, I think these are from the synchronic maps that Lisa and I make for the full sun based on the surface flux transport. But you can see the magnetic fields in red and blue, and the positions of the quarks in black. What you find is that the quarks tend to line up, move along the boundaries of the giant cells. I at one point had a movie of the vorticity pattern where you could see that. I apologize, but it's interesting here with the magnetic field and seeing how these quarks have formed these strings around the poles and spiral in to the along with the giant cells themselves. All right, that brings me to my conclusions. We've improved the local correlation tracking method, and it provides cleaner velocity data, and the differential rotation profile that we use for the giant cells produces more complete velocity maps for the giant cell flows. The flows we find are largely toroidal. They're vortices rather than diverging, converging flows like supergranules. They have left-handed radial helicity in the north and right-handed helicity in the south. We find the two regimes, the polar vortices that persist for many months, and the equatorial Rossby waves with shorter apparent lifetimes. And a lot of that apparent lifetime is that they are moving through each other. And so, you know, just correlating the pattern doesn't necessarily give you the lifetime. The polar vortices transport angular momentum equatorward. They drift poleward and have a rotation profile like that found near the base of the convection zone. The poleward drift at high latitude suggests a meridional circulation with two cells in radius, poleward at the surface, equatorward below the surface shear layer, and poleward again at the base of the convection zone. And the magnetic elements are advected along the boundaries of the polar vortices. So with supergranules, they're advected to the boundaries. With the giant cells and the polar vortices, they're advected along the boundaries. And with that, I'm done and would be happy to take questions.
Wonderful. Thank you so much, Dave. Yeah, let's open up the floor to questions. Either raise your hand or type your question in the chat or in the Q&A. We do have one question already. Todd Hoeksma asked, are the instrumental artifacts stationary in time? Phil commented to be determined, but wanted to see if you had any further comment.
They are not. In fact, we have to do this at, and I think, what is it, there are different focus positions. There's something that and Todd knows this better than I do. There's things that HMI does from time to time, and those features change. So we have different patterns at different times. So are you gathering these, Lisa?
Oh, sorry. Yes. Thanks so much, Dave. I was muted. Yeah, great. Again, if you have any questions, feel free to raise your hand, type them into the chat or the Q&A. Theory asks, how long does it take to reduce one day?
To reduce one day.
Theory, do you want to?
Yeah. Well, no, I can tell you that to do all of it, I do this on I'm retired, so I have a MacBook Pro, and I do all of the calculations on the MacBook Pro, and to do all of that, the 10 years worth of.
Gustavo, can you please mute yourself?
Whoa. All right. So to do the entire 10 years of data took me many months, I think on the order of 6 months, basically running 3 processors day in and day out. So there was a lot of processing involved to do it all.
Okay, thanks.
All right, Gustavo has a question?
I do, but I have a lot of noise in my street, so I can wait a little bit if someone else has a question. Or it's okay for you? It's okay?
Yeah, go ahead.
This is fine.
Okay, thank you, David, for the nice talk. I enjoyed it. I have a question about your Reynolds stresses. In the figure that you present, you are presenting B theta B phi.
Yes. Phi is in the direction of rotation. Theta is from the North Pole to the south.
So this is likely not transporting any angular momentum, because when you compute the angular momentum transport, then you have to multiply this by r sin theta, and that will bring to almost zero the pulse signal here.
But sure, but nonetheless, this is a correlation of prograde velocities with the equatorward flows. That is a flux of angular momentum, and yes, the actual flux, as far as what's the circle that you're going through with that flux is tiny at the poles. Wow. But again, it is an equatorward flux. The fact that it disappears when you get down to the Rossby wave area is a little disconcerting. I would think that it would continue to lower latitudes, and it may be that the Rossby waves are a shell on top of something deeper. I don't know, but again, this is a flux in the direction you need to maintain the differential rotation.
I agree with the sign, but for computing the flux, the level arm is present.
True, and whether you would actually have to put this into to a model to see, how much does this do as far as what does this stress actually do? Yeah.
But I like to see the kinetic helicity, because this gives a positive alpha effect in the northern hemisphere, right?
Yes.
Okay. This is good for a dynamo in the convection zone.
All right, next question. Phil Shear asks, how do you deal with the orbit leaking into the Dopplerograms with a 24-hour and 12-hour periodicity?
That probably comes out when I measure individually the convective blue shift in particular. Because the radial, any radial component to the flow that isn't accounted for in just the spacecraft motion will end up in the convective blue shift signal, and that's calculated for each and every, individually for each and every Dopplergram. So certainly the radial component is taken out that way. The east-west component is taken out with the determination of the differential rotation. The north-south component is not, probably not, well, I guess within the meridional flow calculation, there's the one cell from south pole to north that would take that into account. So I think that temporal variation still gets removed by the fact that I analyze those signals and remove them. On the other hand, related to this point, I still think that what I do to produce the data, all these steps, is probably overkill. That for the most part, you could remove, well, I guess nah, maybe not. I was gonna say you could just remove the disk average signal from each one of them, and you would pretty much get the supergranule pattern. You know, gradients across the disk do influence the correlation method a bit. So this is certainly, I think, the cleanest method to get rid of it, but it may be overkill, that you don't need to do all of these steps, but just remove a disk averaged Doppler velocity image from each one.
All right, great. Nicholas Brummel asks, a bit confused by your final conclusion. Are you saying that magnetic elements are actually observed, or are you equating your quarks to what magnetic elements would do?
The latter. In fact, when I watched this movie, you can see the magnetic elements underneath. They have a different rotation than the giant cells. So the quarks are not moving at the proper rotation rate for the magnetic signal. That was, here, that the magnetic elements at high latitudes rotate more slowly than the supergranules, or the giant cells, I'm sorry. So the giant cells are moving the quarks at a different rate. So there's far more than just the giant cells involved. But if I just look at the giant cells alone and what they do, they would tend to, move magnetic elements along their boundaries and along with the cells as they spiral into the poles. But again, their supergranules are far more energetic, and how they move, I'm sure, influences the motion of magnetic elements even more so than the giant cells. So this is more a tendency on top of what supergranules in particular are doing.
Great.
I hope that helps. But yeah, the latter part of his comment was correct.
Okay. Tom Duvall asks, can you extract information on the flow amplitude versus depth?
Well, I tried to do that with the spherical harmonic analysis as a function of time lag. Again, we only, given these time lags, it's not a huge range in depth. It goes from 20 megameters in to 40 megameters in. But over those, 20 megameters within the surface shear layer, basically the spectrum remains the same. So there's not much change in structure of the giant cells over those 20 megameters within the surface shear layer. Certainly we would like much more. Again, helioseismology certainly gets far deeper than tracking supergranules. So I'll leave that to Tom, for Tom to do.
Great. Todd Huxema asks, do you think anything interesting happens above 75 degrees?
Absolutely not. No, of course it does. yeah, exactly how these things spiral in, what they do. The thing I wonder about in particular in the extreme polar regions is how these vortices might, whoops, come on, right there, is how these vortices might be involved with the polar plumes and the patches at the poles. It'd be interesting to see whether there's any relationship between, you know, the positions of these vortices, the centers of these vortices, and the magnetic structures we do see in the poles. So yeah, certainly I'm dying to see what it looks like up there. I hope I live long enough to see what's happening up there from spacecraft observations that see those high latitudes. So no doubt there's interesting things going on there, and in particular how these flows interact with the magnetic fields there.
Todd follows up with, go Solaris. I think that's absolutely right. We're all very excited to see what's going on at the poles. It's definitely going to be something very interesting and very beautiful. I don't see any other questions in the chat or in the Q&A. I don't see anybody else raising their hand. Oh, there's Shay. Shay has a question.
Of course I do. So I'm noticing in these videos and some of the other ones that you're showing, there's sort of a clear rotational element that where everything just gets a little bit later. So like the rotation decreases everywhere and then kind of increases again. I'm guessing that is just some kind of systematic effect, but is there some other?
Yeah, I don't know of any changes in the differential rotation with time on this. It may be the movie was a little glitchy as far as hesitating at spaces, but again, I think the only artifact I see in this that's glitchy is this, the far side of the sun getting readjusted as it gets observed.
Yeah, that may be what I'm seeing.
Yeah, so there is, in particular, if you look at even at the equator, you'll see this band moving across, and that's the far side of the sun, as those velocities get updated by more recent observations than 17 days away. So in particular at the high latitudes, nominally the far side of the sun from where it is at the day in question is data 17 days earlier and 17 days later that goes into making that. And there's no doubt that these things evolve, albeit slowly, they evolve a little bit over those 17 days. So as that comes into view, the flows get adjusted to what they really are.
All right, I see Junwei has his hand raised. Junwei, did you have a question?
Look at this video. This reminds us the unipolar magnetic regions in high latitudes. We also know that these unipolar magnetic regions also swirled into polar regions. So what I'm wondering is there any relation between these giant cells with those unipolar magnetic regions, or how do they interact with each other?
Good question, and had that thought ourselves early on. So we tried to correlate this pattern with the magnetic pattern, and it doesn't correlate very well. I think most of the spirally unipolar things you see are purely flux transport, primarily by supergranules and how they move. So you take active regions and the high latitude bits of active regions and move them off towards the poles and spread them out with supergranule diffusion, and that's how those things are produced. Again, we early on, and I probably ought to do it again, early on we tried to correlate these flows with magnetic features and really didn't find anything worth talking about.
All right, Phil has a question.
Yeah, I wanted to first thank you for the talk. Really, really interesting, really nice work. Then I wanted to just add a side comment that I understand that there'll be something interesting coming from MPS in astronomy and astrophysics maybe tomorrow. So it's very highly correlated to this work.
Oh, really?
All right, well, I guess we'll all have to keep our eyes out for that.
We wait with bated breath.
Okay, any other questions or comments? I don't see anything else in the chat. All right, David, wonderful talk. Thank you so much for giving us a beautiful seminar. Fantastic questions all around. If everybody could join me in a round of applause for Dave. Thank you so much.
Thank you. It was my pleasure, seriously. It's good to see all of you, or it's kind to see all of you guys again. It'd be nice to see you in person at some point.